Welcome back. And we had a request for some mechanisms, so I figured let's do the ones we haven't done. In this mechanism here called the Edman degradation. How do I know it's the Edman degradation? Well, it's got phenyl isothiocyanate. That's the chemical for the Edman, and it targets the amino terminal residue. So all the other residues, and let's see what gets clipped off. There's the carboxylate, the NH. Looks like the NH becomes an NH2, so I don't think you want to short form that out of the equation. There'll be some chemistry going on when that thing leaves. And there you go. Gonna need a lone pair on the amino terminal nitrogen, and we're gonna call this R. Never to draw it again, which is really nice. And we're gonna do all day, red first, blue second, and I got ambitious. We probably have more than we have time for, but if we have time, we'll do this one, red first, blue second as well. And probably not time for the DCC, but that's an easy mechanism. I really know you can learn that one on your own. I strongly suspect everybody can learn all of these on their own. Lone pair attacks the carbonyl of the phenyl isothiocyanate. N being more electronegative than S gets to be N minus. And we'll go from there. N minus. That N minus needs to attack something, doesn't it? And let's see what happens. We've got our proline group here, NH plus. Carbonyl. Not from there. We have a new bond to C double S with an N minus and a phenyl. Okay. All right. So the N minus attached to the copper double bond to sulfur, N minus ends up bonded to a carbonyl. It's got to be that carbonyl, doesn't it? Can we do that now? Why not? We have HOET that can take care of our deprotonation needs. Probably want to do that first. Then we have N minus that can come and do its thing on a carbonyl. And then we can have our leaving group leave. If we have this set up, which we do from the red arrows, oh, I'm starting to like it a lot. Didn't we just make this with the red arrows? Let's kick off our leaving group and be done with it. Green, third color. Can't leave until it protonates. And let's see what we have. You know, I forgot something. I haven't done this mechanism in a long time myself. I remember you got to make a ring with sulfur inside the ring first. The sulfur ends up inside the ring. Then you have to open up the ring. Yeah. Well, it's something I forgot. but I haven't studied this in a long time either. So what happens is the N resonates, sulfur attacks that carbonyl, electrons up, that's still fine. Then they come back and you can still use your protonated ethanol. Step 3. Now let's come up with a protonated ethanol. Green arrows. 3rd step. Understood. H protonates. So one of the pieces is already accounted for. That piece. This is NH2 attached to R. And we have a ring now. And let's see what we have. We have the nitrogen in a pyrrolidine. And we have a red bond from nitrogen to carbon to sulfur. There's now a double bond N-F up there. And there's a new bond to a carbonyl. Carbonyl that's blue because it was already a carbonyl. And we have that ring. That's not our product, is it? It's got to open up and then reclose with the nitrogen instead. So how does that happen? We're going to use ethanol as a nucleophile. And it's conjugate acid if we need it again. Acid-base pair. See what happens. There you go. Red first. Pop it open. Second step. Come on. Reestablish carbonyl. This resonates to make an N minus. And that N minus is going to attack our carbon with a leaving group on it. Didn't need the oxonium yet. So we do have a carbonyl. There's OH ET, nitrogen, it's bonded to a carbon that has an N minus, phenyl, double S. That looks a little more like the product, doesn't it? We can finish it off. Red arrows first. Baby blue next, and I think we're done. So ethanol, like a ring opening catalyst there, isn't it? Pops open the ring, serves as a leaving group here, makes the ring here. So it goes, let's see, N-phenyl attached to carbon double bond sulfur, the same carbon attached to nitrogen. N-phenyl attached to carbon double bond to sulfur, same carbon attached to nitrogen. It's in the ring, comes around to an alpha position, alpha to a carbonyl. Beautiful. And that gives that. That's a fun one. You gotta make a ring that's not the right ring, open it up, and then make the right ring. Don't try to shorten it. I saw a shortcut. That's what I was trying to do over here the first time. Then I remembered it doesn't go that way. They've studied this mechanism thoroughly, and it makes the other ring first. As soon as you see cyanogen bromide, you target methionine right here. And look at the parts that don't change, because that tells you what you're allowed to circle. Let's see. It's carboxylate, carbonyl, NH. That didn't change. So I think everything up to here is cool for an R. And it's a new problem. You can still call it R. Let's see that ever changing. And this one always starts like this. How are we doing? We're doing okay. We'll get this one done for sure. We're going to attack, carbon. And you want to just boot off the bromine, don't you? Don't do that. You got to break pi before sigma. Why did it go towards N and not towards Br? Because one, N's more electronegative, and two, I want to break pi before sigma. And then we have our comment up there. Lone pair on N can resonate back. Second step. C triple N is reestablished. Br minus is done for the day. And now we have R attached to, don't turn to green. I don't like green. I don't have anything against green. Cyanide. What's the third bond to sulfur? A methyl. Oh, I see that product. Then we have, I'm going to do something here that's, I don't hope it doesn't throw you off. Put the O down there and the NH here. I don't see this changing either. There we go. Phenyl up to phenyl, CH2C, CO2 minus. That doesn't change. All right. Now we got to make a ring, lactone. Actually going to make an iminium version of the ring and then do hydrolysis. What do I mean by that? Make an iminium by resonating in nitrogen. This just doesn't look nice. I want it to look nice. It's our last thing. Just need a little longer bond there. NH, lone pair, R prime up there. This will just look better. Resonate in to make a double bond. O minus, it does a backside attack on a primary carbon with a nice leaving group. Gives us two things. That's one of them. And the other one is a iminium version of a lactone, which after hydrolysis will become our lactone. We could have saved a second. That H has to go eventually. No, we need H's on there. Getting greedy. Sorry. Don't get greedy. Doesn't that look a lot like this ring here, except it needs to go hydrolysis to get there? It does, and will, and does. H2O. And we got a lot of H2O. Now I can get greedy. After that, you'll generate an oxonium. Do you agree? I hope so. Second step, neutralize the oxonium. Moving right along. I think we're ready to just do a elimination. call this a day. This is going to venture off to this piece and this piece. What needs to happen? We need a water, take an H, oxonium, which you just made, to provide an H. You want to protonate first to make it a better leaving group? Then do your elimination. Very consistent with what we've been doing all semester. And you're done. That's good. And I don't want to just ram through this DCC coupling, but it's not as hard as it looks. Look over the answer key. Look over the answer key for this too. There's some review stuff in there where we're getting rid of a benzyl group using hydrogenation. Called that hydrogenolysis. And yeah, look over the answer key. I'm sure you guys can figure that one out. And that is the end of our lecture segment for this semester. It's been a tough semester for everybody, and I'm glad we made it through. Just one little push for test 4. Some of you really need it to make sure your grade's solid. Others can slack off a little bit, but it's good experience to do test 4, even if you don't really need it. And send me emails if you got questions. Once again, no problem set 4. That's been canceled. So everything you do on Monday is your test 4 score. And email me with questions if you have any. All right. Take care of yourself, everybody.